welcome to the afternoon session. We will have 3 talks in this session, 30 minutes for the talk and then 10 minutes for questions. Is that, no? 30 plus 10?
No, 35 plus 5.
Okay, 35 plus 5.
Oh, 25 plus 5.
20, so I'll give you a warning at 25 minutes.
Okay.
So the first speaker for for this session is Rick Watkins, and he will tell us about the large-scale bulk flows.
Okay.
So,
is this working? Can you hear me? Yes? Okay, so I'm going to talk about my some recent work I've done on understanding the large-scale bulk flows. Thank you for inviting me to talk. First thing I'm going to do is just acknowledge my collaborators. I've been working with Hume Feldman for a long time, and Brent Tully was involved in this project as well as a bunch of undergraduates, both at Willamette University and at University of Kansas. Okay, so first off, just to introduce people to bulk flows. So first off, we talk about peculiar velocities. Are the velocities of galaxies are clusters that that are separate from the Hubble flow. So we talk about the redshift being a combination of the cosmological redshift and the Doppler shift. And so to calculate the velocity, all we need to do is measure the distance and subtract h0r from the redshift. Of course, I'm oversimplifying incredibly here. Okay, so some of the challenges to working with the peculiar velocity is, one, we can only measure the radial components of velocity. So we only have one component of that 3-dimensional velocity. The reason that I work in this field, and I've been working in this field a long time without as much competition as you might think, is because this data is incredibly noisy. And so it's really challenging to work with the fact that you've got uncertainties as large as you have. And these are coming from the distance uncertainties. The redshift is measured very accurately, but the distance is very difficult to measure. Another fact that we need to deal with is the fact that the velocity field is only linear on larger scales. And so we don't want to look at the small scale motion, so we want to focus on the large scale motion. So the bulk flow is one way to get around these challenges. So bulk flow, basically we take a volume of radius r, and then we just average all the velocities inside that volume. Okay, so the bulk flow, a lot of people sometimes in papers, they talk about the bulk flows as if it's one thing, but the bulk flow is measured for a specific radius r. So we're going to have, there's not just one bulk flow. We need to have some kind of control over what the radius of the volume we're looking at is. Some of the pros of the bulk flow is it averages out these large measurement errors so we can get reasonable uncertainties on our bulk flow values. It averages out these small scale linear motions. Provides a test of the Copernican principle, so we expect that if everything, the cosmological principle, so we expect that if everything is going well, the bulk flow should be decreasing with radius. And then another another thing you can do with the bulk flow is you can measure it independently of the Hubble constant. And this is kind of important given that we've got the tension in the Hubble constant. We're not sure exactly what the value is. But the way we measure the bulk flow, it's completely independent of what value of the Hubble constant you use. And the disadvantage of the bulk flow is it reduces the information down to 3 numbers for a given radius. So you've got this, 30, 40,000 data points, and you're reducing them down to these 3 numbers. Okay, so the way we measure the bulk flow is we measure it as a weighted average over these radial velocities. So we just have these weights, and they multiply the radial velocities for each object, and those add up to be the bulk flow components. So we've got the x, y, or z components. Now, there's an interesting thing you can do here that if you assume that the velocity field is a gravitational potential flow, so it's curl-free, then you can write things in terms of velocity potential, so there's only 1 degree of freedom in the velocities. And that means you can actually calculate the bulk flow, which is an average of the 3D velocities using only that 1 degree of freedom, using only that radial peculiar velocities. And so it turns out that if you use these weights, if you had an ideal survey, which was just you really sampled the volume well and evenly, then if you just use these weights, you would actually estimate the full 3D bulk flow using only the radial velocities, just because there's only 1 degree of freedom because of the curl-free condition. Bulk flow still works even if the velocity field isn't curl-free, but it's just, if it is curl-free, which is the usual assumption made, then it's nice to have this interpretation of the bulk flow. It's a little bit surprising that you actually weight by the inverse of the distance squared, but it works. We've tested this, and it really does give you the full average of the 3D velocities. So this is for an ideal survey. What would you do if you didn't have an ideal survey, which we never have? And if you have a real survey, they're going to sample the volume unevenly. And in particular, you have this problem where most of your information is nearby. So your uncertainties are really growing quickly as you go to a larger radius. And so if you just did sort of a naive calculation based on information, you would focus on the inner part. You'd focus on that small distances because that's where the information is. And that's also where you have most of your galaxies. So you have to take this into account if you're going to measure the bulk flow on larger radii. It's also the problem they're unevenly in space, as you're going to see when I show you a map of the survey we're using, that you need to even that out as well. So you need to even out the spatial part, you need to even out the information, and also you tend to have a lot of galaxies clustered. Since galaxies cluster, you have a lot of galaxies in one place around a cluster, and so you want to even that out as well. So you want to try to sample the volume as well as you can to make it as similar as you can to the ideal survey that you can't obviously make. And so we came up with this minimum variance method, and it basically generates weights for us to calculate the bulk flow that result in a bulk flow that the estimates of the bulk flow we're coming up with are as close as possible to what you would get from an ideal survey. So it basically evens out your survey. So you got all this information in the center, and so it downweights the center and upweights the outer part. You've got more information on one side of the survey than the other, and it just balances it out. So it downweights regions where you have lots of information and upweights regions where we have less, in order to have a uniform sampling of the volume so that we can get as close as possible to actually measuring what we say we're measuring, which is this bulk flow. Okay. As an extra bonus, I can add Lagrangian multipliers into the method and actually make it completely independent of the Hubble constant. And that makes sense because the Hubble constant, basically if you get the Hubble constant wrong, all you're adding to your velocities is a phantom radial flow. So you're either adding an inflow or an outflow, and so that shouldn't show up in your bulk flow because the bulk flow shouldn't contain anything about radial flows. But if you're not doing something like the minimum variance method, and you're not evening out your survey, then a radial flow could change your bulk flow. Yeah?
The radius you're defining is a co-moving radius that is based on some Hubble that you've chosen as how you're moving, but some cosmology that you've chosen within which you're. If you change the Hubble too much, wouldn't galaxies potentially go in and out?
Well, we're measuring the radius of the volume in h inverse megaparsecs, so it's independent of the Hubble constant.
Yeah, it's moving with. Sorry. Yes, with a particular choice of cosmology, or you're not doing that. Like, how do you choose? Because if you right, so now if you change the Hubble too much, shouldn't that change?
Well, so we're basically in the regime where the Hubble laws is still linear, pretty much.
I think the number that you
No.
attach to that R
R,
is
yeah.
right. That will have a linear
Different,
symbol.
yeah.
But that doesn't matter. They've chosen some physical volume to look at. What you decide to call it, whether it's 120 H inverse or 130 H inverse.
I see what
that's
you're
just the
saying,
data.
yeah. So since we're placing the galaxies in space using a redshift, and so that is naturally in H inverse megaparsecs, and so you're going to measure a volume in H inverse megaparsecs, and it shouldn't matter, it doesn't matter what the Hubble constant is. And oh, that's another good point, is that when you calculate what the expected bulk flow is from theory, that's also independent of H, because you can scale it. It scales in a way that if you use distances in H inverse megaparsecs, H drops out of the calculation. So your estimate matches your volume that you're using. Not your estimate, your prediction.
But you do have to specify if you're using a top hat or Gaussian, what kind of smoothing you're using.
So we're actually using the definition of bulk flow it's a top hat essentially. We're using a sphere with a sharp edge, which is what people think of, I think, when we played with different things, but the sharp edge works just as well as anything else. Okay. All right, so we've got something that's independent of the Hubble constant. And it makes sense that we can do that because of the fact that the MV method flattens out the angular distribution. So radial flows aren't going to show up in our bulk flow. They'll just cancel out. Okay, so just to show you the catalog, we've got 38,000 galaxies and groups of galaxies. So the CF4 has a singles catalog and a group catalog. I used the group catalog. So some of these points are actually groups of galaxies. It includes the SDSS, the 6DF. Oh, yeah.
So what happens to the error? I didn't see that. Like, if your error is bigger or smaller for your measurement, does that go somewhere?
For your
For
velocity?
your velocity, yeah.
Yeah, so the error is factored into those weights.
It's in the weights. Okay,
Yeah,
I
because
see.
the method is trying to match the ideal survey. And so it takes into account the uncertainty in the velocities as well.
Okay, so the weights have the errors. But then is that just assuming uncorrelated errors, or is just correlated errors? Or doesn't matter?
They're uncorrelated pretty much.
They're uncorrelated,
Yeah,
yes.
the individual velocities are uncorrelated.
Okay, thanks.
Yeah. All right, so we've got this distribution on the sky. You can see it's very anisotropic. This is the 6DF survey up here that's been added to the...
Sorry, if that is the case, then are you not weighting towards the nearby galaxies which are better measured?
Well, so what the method is doing is it's smoothing out the information.
Yes.
So the uncertainty is telling it about the information.
Sure. But as you said earlier, the more distant galaxies are more
So-
clearly measured.
So
They
if,
will contribute less to the weights.
well, so it upweights those to get an even sampling of the volume to compensate. So the weights compensate for all the unevenness of the survey. So you actually get something that mimics an even distribution of galaxies. Okay, so you can see we really need something like the MV method because this is a very anisotropic collection of galaxies. And so one way to think about this is to look at the x, y, and z distributions. So this shows x greater than 0, x less than 0. And then you see the place where it's really different is in the z. That's kind of clear from here that you've got a lot of stuff in the plus z and not as much stuff in the minus z. So that is the biggest difference. The x and y are pretty evenly distributed, the two hemispheres, but the z is very unevenly distributed. And so one thing you might worry is this uneven distribution could feed into your bulk flow, but we don't actually worry about that because it turns out that our z component of the bulk flow is actually small, and it's quite consistent with expectations. So this is comforting, the fact that in the x and y, we get our biggest component in the y direction. And so it's comforting that the y direction is fairly evenly distributed across the volume. Okay, so this is now moving on to work I've done recently. So I've been using these Carrick et al. Reconstructed velocity model of the region within 200 H inverse megaparsecs. I've recently discovered, been told actually that there's a model that supersedes this, but I haven't had time to plug it in yet. So they basically take the mass distributions from the 60F redshift survey within all the galaxies within 200 H inverse megaparsecs and predict the peculiar velocities from the mass distribution. And so this includes the effect of the Shapley concentration, which is sort of the biggest collection of galaxies that we know of in the local universe. And so basically they use, we use their model to predict the velocity, the part of the velocity, the peculiar velocity that's generated by sources within 200 H inverse megaparsecs. So I call that V int, and then the rest of the velocity is going to be Vx, which would come from mass concentrations outside this. So here's the paper just went on the archive in the last few days.
That model itself also fits a Vx because...
Yes, but I'm going to talk about that. Okay, so our model is basically each peculiar velocity is a combination of V int, Vx, the uncertainty, and then we add the sigma star. It's an additional error that represents the deviation of galaxies from being perfect tracers. So it doesn't make much of a difference, but it's traditional to add that there. Okay, and we're going to assume that these contributions here are uncorrelated. And so what we do is we take a weighted average of the peculiar velocities in bins of V int. So we take all the galaxies that have the same V int and do a weighted average of those V ints, and then plot that average versus the V int of the bin. So these are binned. We bin them to use an equal number of galaxies per bin. That's why the points don't look evenly distributed here. And what you see is kind of amazing that we get a very nearly perfect fit. The averages really do lie on a line of slope 1. So this tells us that we're doing something right, that the Carrick is doing something right, we're doing something right. When you think about the fact that these galaxies, the peculiar velocities were calculated using completely different methods and data, it's remarkable that we get this kind of agreement. I do have 2 parameters I can adjust, and this method gives me these parameters, so I can adjust beta, which is the amplitude of the velocities, how you turn the mass distributions into velocities, and then also I can adjust the H0 used to calculate the peculiar velocities to get this fit. So my bulk flow calculation doesn't depend on the H0, but this does depend on the H0. And so if you use the wrong H0, it would tend to slide this line up or down. So I can use that to figure out just what is the H0 that I should use to calculate peculiar velocities in the CF4. All right, so that's kind of an amazing agreement there. You might worry that's dominated by nearby objects because I'm weighting by 1 over the uncertainty squared. So you might worry, what about distant objects? And so I just do a cutoff. I say, what if I only consider objects further than 120? Now we only go out to 200. We're only keeping all the objects in the survey from less than 200. So this is more than halfway out. And you can see we still get really good agreement between the binned averages and the V internal of the bin. So obviously the error bars are bigger because we have more uncertainty, and there are fewer, I think, yeah, I use the same number of objects, so I get fewer bins. Okay. So what happens when you do this is kind of interesting. So the blue is the internal velocities. So that's, I now can calculate the bulk flow due to internal sources, the bulk flow due to external sources, and the total. And the total is what we were getting before. And you see it's a little bit weird that it drops and then rises. But when you subtract out the internal flow, you basically get a monotonically increasing bulk flow with distance. So remember, the expectation is, the standard model expectation is this red dashed line here, that the bulk flow should be decreasing as you increase the radius of the volume. But instead, we're getting this monotonic increasing bulk flow here. There's not much going on in the x and the z, all the actions in the y. And you can see that that's also true for the internal bulk flow. But and this is probably due to the Shapley concentration, the internal bulk flow. But you can see it drops off and gets pretty small by the time you add out to 200 H inverse megaparsecs. But the green line is the external, and that's keeping rising. So that's pretty much rising monotonically as you increase the radius, which is kind of strange. So the external bulk flow increases with radius, so we don't know. And the other thing that this tells us, which is maybe kind of obvious, is that the large bulk flow we're seeing is coming from distances greater than 200 H inverse megaparsecs. So that, whatever is causing this external bulk flow has to be out beyond 200 H inverse megaparsecs. Oh, yeah.
So this is from fundamental plane. Where does this lossless come from?
They come, okay, so the CF4 is sort of a mixture of all available, I didn't mention that. It's a mixture of all available peculiar velocity data. So it includes all the different methods. So half of it, roughly half of it is fundamental plane, half is Tully-Fisher. I've done tests where I've taken out all the fundamental plane, I've taken out all the Tully-Fisher, and the results agree with each other.
Aren't you using supernova data?
And supernova data is in there, but it doesn't make, there aren't as many supernova. So they don't make as big a contribution. It's also using SPF, whatever is around is thrown in. So it is, but when they created the CF4, they tried to normalize all the methods. So they picked like clusters that had galaxy distance measurements from several different methods and used that to calibrate all the methods.
Okay. Thanks.
Okay. How much time am I? 14 minutes. Oh, okay, I'm going too fast. Okay, it's unusual. Yeah, you guys can ask more questions if you want. Okay, so just to finish up talking about the chi-squared and the probability in particular, we can calculate, just using a chi-squared, we can calculate the probability of the bulk flow as a function of radius. And you can see that as r increases, the probability, this is a logarithmic scale here, the probability is decreasing rapidly. So the inconsistency that we're finding only appears at sufficiently large r. And so you only, if you're focused down here, you're not going to see a disagreement with the standard model. You're only going to see it if you push out here. Now that goes, it's complicated because when you're trying to calculate for a large r, it's really important to know how you're sampling the volume. So if you're just using a method that doesn't control that, then you're going to emphasize the nearby region. So you're going to essentially have an effective smaller r for your bulk flow if you're not careful to somehow flatten out or smooth out, not smooth, get the sampling of the volume. If you don't even that out, then you're going to basically emphasize the smaller r because that's where the information is. And so people who claim there's not a problem, there are papers that claim there's not a problem with the bulk flow, that it's consistent with the standard model, and that's most of those cases you could point to. I can say, oh, their bulk flow is a smaller scale than they're saying, or that they don't quite, sometimes people just don't quite understand how the information is being used. So since all the information is at this small radius, it's easy to not see this. So it's not, in some ways it's not surprising that this method is seeing a conflict since we're seeing out here, whereas other methods don't always. There are other methods that claim there's no conflict with the standard model.
Can I ask a question?
Yeah.
Related to what Sukhir was asking. Further galaxies have poorly measured velocities. Shouldn't I see this at least in the error bars also increasing at larger R in your recovery?
Yeah, the error bars, surprisingly enough, they are getting bigger out there. But there's also another thing to keep in mind is we have this, the ideal survey still goes like 1/r². So it's not getting as bad as quickly as you might think.
Is this happening because of the difference between momentum and velocity? Can I look up
The 1/r²?
Yeah, because I want to measure velocity but not momentum. If I don't have the 1/r², I'll weight the outer volume more.
No, the 1/r² is coming from how you convert radial velocities into components of 3D velocities. So if you just take that full radial velocity, you actually oversample that region. So this 1/r² is the conversion between having one component averaging over one component and averaging over the full 3D velocities.
But that's just a factor of square root of 3 or something, 3 by 2.
Say it again.
Let me think about it.
Okay. This helps in terms of, because the uncertainties are getting quite large out near the edge. But this means that that problem is not as bad as it could be because we're downweighting those velocities naturally in this, although we're upweighting them relative to what you would do if you were just looking at the information. Yeah?
In an ideal survey, as you go out, there will also be an R² scaling on the number of sources. If that's something you want to,
Yes.
is that something you're attempting to account for? Using
So since we're trying to mimic the uniform distribution, that 1/r² means you're basically taking spherical shells and weighting them the same. And so we're doing the same thing. Our weighting mimics that. So if you've got fewer galaxies than you would have, you upweight them because of that. So we're making it so our weights mimic the ideal. Yeah? Let's see, the velocity bias. Yeah, we haven't accounted for that. That's something I should look at. We're basically taking the CF4 at face value. Gotcha.
But I thought the selection function is accounted for here because you're uniformizing your distribution.
Yes.
Like sort of inverse weighting the selection.
Right.
But is it luminosity? Is it luminosity limited by luminosity or by magnitude, by flux?
So that's a complicated question because the CF4, just like I said, it just adds all the surveys that are out there, and so it's neither magnitude limited or
I mean, it's
redshift
relatively
limited.
shallow in redshift, so maybe these effects are small. But yeah.
Yeah, I think because we're not going so deep, I think we're not. I think these questions are bringing up a lot of why these deeper peculiar velocity surveys are going to be really complicated. This is child's play compared to what it's going to be when you have to deal with greater distances. All right. What I want to talk about, what I want to finish on. So again, the problem only appears at larger distances. At smaller distances, you really don't, smaller radii, you don't have a problem. Okay, so basically the probabilities we're coming up with for 150 and 200, we're getting down to like 10 to the minus 4, between 10 to the minus 4 and 10 to the minus 6. So it's a serious tension with the standard model. Okay, so one thing I've thought a lot about is how do we explain an external bulk flow that increases with radius? That seems like a really strange thing to have a bulk flow that increases with radius. But the way to answer that, the way to think about this and understand it, is to stop thinking of the bulk flow as a dipole. So if you think of it as a dipole, then you've got this problem because you've got this big volume moving through space like this, and this volume inside of it around us moving in the opposite direction. That's the only way to explain it if you think about it as a dipole. But what you need to do is just let go of the idea of it being a dipole. And one way to see that that's actually a very productive way of thinking about it is to actually, I can take my contributions, I have my weights times my radial velocities, and I can look at where the contributions to the bulk flow are coming from within the volume. And what I find, so this is in the direction of the bulk flow, and this side is the side of the sky where the bulk flow is going, and then this side is the opposite side. 0 is where we are. And what you see is that there's a very clear, and there's not many galaxies out here, that's why it drops down like this. But what you see is a decrease in the contribution going across the volume. So this does not look like a uniform flow within the volume at all. And usually the bulk flow is modeled, like the external velocity in Carrick et al., is modeled as a uniform flow throughout the volume. So this calls that into question, that assumption that the external velocity can just be modeled as 3 components of a uniform bulk flow is not really correct given this picture. What this looks more like is there's some big object out here beyond the survey that's pulling on the galaxies closest to it, and then that influence falls off as you get further away from that big source. So once you think about it that way, it seems kind of clear that if you've got some external object, some big external mass concentration, it's going to affect the objects closest to it on the edge of the survey more than it's going to affect the whole volume. It's not going to create a uniform bulk flow throughout the volume. And so I think this leads to an idea that we need to sort of rethink how we model the external bulk flow. I've seen a lot of papers that just model it as a uniform flow, and this shows that it's not really that way. Yeah?
There's a logical consistency issue with your method now, because you're using a re-int from the Carrick et al. Method, which models it as a uniform external bulk flow, right?
Right, but my understanding was that the Carrick, that it wasn't that sensitive to that assumption. But I should probably go back and look at that.
Also, in your previous plot, your bulk flow from your method at 200 H inverse megaparsec, that value is in more than 3 sigma tension with the Vx of the Carrick et al. Model, which is 159 plus or minus.
Right.
Right.
Well,
so
it makes sense that it's going to be in tension with the Carrick model because the Carrick is just the internal.
Yeah, okay, so the
Carrick is just taking the mass distributions within 200 megaparsecs. It's not modeling the mass distribution outside of 200 megaparsecs. So it should not see a big bulk flow.
Okay.
So I don't think the external, the dipole that they put in their model actually affects things very much. Okay, that's right. I'm sorry. Sorry to say ooh. But that external dipole only comes in when they compare it to velocity surveys.
Yeah.
They compare it to other velocity surveys. But I'm just using the values they calculate from the 60 dF mass distribution, which isn't dependent on the external bulk flow. They only introduce the external bulk flow when they compare it to velocity surveys.
They use the 2m plus mass distribution, not 60.
Oh, yeah, sorry. Yeah. All right, so that's basically,
So before you
Oh,
go,
yeah.
you said there could be something pulling us from outside Shapley.
right,
So you're already talking about 300 megaparsecs, and if I do a simple
yes,
estimate of
it's big,
what mass I require,
yeah.
it's 10 to the 17 solar masses.
Thank you for asking that, because I need to say a couple
Where
things
is
about
this
this.
guy?
Okay, so one thing, that sounds great. I just was emailing
it's
with,
obvious thing to think,
with
but,
Brent
you know, yeah.
Tully about this, and he was like, how do you hide something like that? Well, the way you hide it is it turns out that my bulk flow is pretty much in the galactic plane. So this, whatever mass distribution it is hiding behind the Milky Way.
Not in the infrared. You would be seeing things in the infrared galaxy, dust extinction don't matter so much then. I mean, I'm not an expert. Astronomers here can come
Yeah,
in,
I'm
but I
not.
believe you can, in 2MASS and other infrared surveys, see pretty much through the galactic plane.
Yeah, yeah, so it is, I mean, yeah, so I'm just putting that out there as something
It would
that's
have to be a
possible.
completely dark lump with nothing in it that is visible or shining.
I'm not sure about that, but I was gonna say that this does not look, this also is interesting in terms of, there are two possible explanations for a large bulk flow. One is a anomalously large mass distribution, but the other would be like either we're using the wrong cosmic rest frame or a tilted universe or something like that. But this doesn't seem to look like you would get from either the tilted universe or using the wrong rest frame. And in fact, there's been the recent work with a radio source dipole and Seacrest work with Sebastian's going to talk about this.
Yes.
And that they see the same thing. They get the direction of the CMB dipole, but a different amplitude. So I thought about whether that could explain our result, but the CMB direction is too far from this bulk flow direction to.
So 20-something degrees here.
It's actually like 45
yeah,
degrees, which is too big a
I'm talking
difference.
about a dipole,
Yeah.
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 If I'm looking in the direction of the galaxy and the opposite direction, then extinction is completely different. So if you just kind of, your normalization of fundamental plane, or basically the way you measure magnitudes or colors are different on one side compared to the other side, that can give you an isotropy, right?
Well, so it's important to realize the direction is in the plane,
Yeah.
but where the contributions are coming from is actually out of the plane.
Sure,
So
but
we
there
don't
is
have any objects in the zone of
but there is
avoidance.
much more dust on one side than the other side, right? There is much more extinction on one side than the other side, right?
Well, if you have, that would be a north-south extinction. That would make a Z component of bulk flow, right?
No, if you're looking towards the center of the galaxy,
Oh, toward the center versus the other
but
side.
the opposite direction. There's more
Right.
extinction on one side than the other side, right? So the question is then if the normalization of basically your fundamental plane or targeting for sure would be off because one side is the extinction, has more extinction. Of course, you try to correct for it, but the question is that enough, right?
Right. No, that, yeah.
Have you tried separating Tully Fisher and fundamental?
Yes.
Doing separate?
Yeah, I get the same result if I separate those two.
That's interesting.
Okay, thanks.
Yeah. All right, did I leave any time? Time's up, yes.
So here you're measuring the mean bulk flow.
Yeah.
Do you have enough signal to take shells and measure the two-point function? So basically the velocity power spectrum as a function of distance, because that could be a way of checking that things are behaving. So you subtract this mean,
Right.
and then you check that your velocity correlations are consistent with what we expect. Do you have enough galaxies to do this?
Yeah, I've tried things like this, and there's not enough information to really nail it down.
It's too noisy, basically.
Yeah, the data is so noisy.
So we should thank the speaker for the talk. And since we already had a bunch of questions, maybe one last quick question.
Yeah, yeah.
So there was the interesting question about the delta V squared compared to the bulk flow. But another interesting one, of which there must be good optimal estimators now, is Hij, the tensor. And And that seems to go hand in hand with this whole situation. And there's an interesting aspect of, as you go out in scale, one feeds into the other. And so you can perhaps get a consistency check.
Right.
Anyway, I wonder
No,
if there's
should
much
think
work
about
on that or not.
Yeah, you're seeing that HIJ, and it's definitely in your talk sparked my.
Well, it's a natural thing, and you know, this is one of the reasons that I'm skeptical about the supernova people, because and Adam Rees and company, because they never look at any of the anisotropy, and they should.
Right.
Here.
Yeah. So I that's a good project that I can work on.
Okay, so then let's thank Rick for this talk. So our next speaker is Sebastian. Our next speaker is Sebastian, who will tell us about the cosmic dipole anomaly.
Okay. 10-minute warning at print. Super. Thanks. This works, right? Yeah. Can you hear me? Super. Thanks, everyone, for being here. Thank you, of course, especially to the organizers. This is my first time in India, so this is exciting for me in many ways. I hope this works in the way I expect. Yes, so I've been asked to speak about the cosmic dipole anomaly, one of the many anomalies that we'll hear about in this meeting, and one to be added to the list of the anomalies that are perhaps a bit threatening to the standard model that we entertain currently. I list here the work of a subset of the collaborators that have contributed quite a lot to the work I've been involved in over the last years. I'm going to try to give an overview of the things from our perspective, from the work that we've done, but also to sort of explain to you what this is about entirely. So what this is about is really the cosmological principle. Subir already explained what this cosmological principle entails and how central it is to our cosmological model. Really, just to summarize, one could define it as the principle that says all physical quantities measured by a co-moving observer ought to be the same in every direction and at every position. Usually the statement is backed up by a picture of the CMB, like we see it on the right. Apart from perhaps some of the large-scale anomalies that Glenn might be speaking about, this picture really is a picture of a quite isotropic distribution of temperatures. A fluctuation of 1 in 10 to the minus 5 really is small enough that we can say statistically the CMB should be isotropic. Is this enough to justify the cosmological principle? This was a question that was addressed by Ehlers, Guerin, and Sachs, and some following papers starting in the 60s, who said that not just one CMB, but in fact all CMBs should be statistically isotropic. All co-moving observers in the universe ought to see a statistically isotropic CMB in order to justify the Friedmann-Lemaitre or Robertson-Walker metric. And we have a problem. We're just one observer. We're not all observers. And we're not even co-moving. And we're not co-moving as we see from the CMB dipole. At least usually the CMB dipole is interpreted as due to our motion with respect to the frame in which the CMB photons would be observed to be the same temperature in every direction. However, we see a dipole in the sky that is of order 10 to the minus 3, which we can interpret as due to our being boosted towards this rest frame of the CMB with a velocity of hundreds of kilometers per second. So we can't answer the question sort of demanded by Ehlers, Guerin, and Sachs. We can't be all observers at once. We can try to be one co-moving observer by interpreting the CMB dipole as fully kinematic. And then what we're left with is a consistency check. Can we look at other observables of our observer boost and check whether these observables are consistent with the picture that we see from the CMB dipole. So this is something that really refers to how things move, and so how things move in our local vicinity is shown by this plot here by Baru et al., which I like to show. On the left-hand side, you can see a density field. In fact, it's a slice through the supergalactic plane of our local density field. That shows in red the overdensities that are the superclusters, Virgo, Norma, and Shapley. I hope you can see them. It's maybe hard to tell from the color scheme. In the center of it, I can probably point towards it here, there's a small cross, which is our location. So really, this is just from our vantage point, the local density field. And these overdensities, due to gravitational attraction and gravitational infall, lead to a velocity field, which you can infer from these observations. In this case, this is a radial velocity field on the right-hand side, where you see exactly that. You see an infall of matter towards Shapley in red, and you see also an infall of matter towards Shapley from the other side, but in blue because it is a velocity pointing at us instead of away from us. And so you can reconstruct this field. Something that you also see refers to the talk we just heard, which is that the left-hand top left corner is tinted a bit orange, and the bottom right corner is tinted a bit blue. This is this external velocity field, bulk flow that the Carrick et al. Field contains, and that is such a homogeneous flow that Rick just mentioned. So here it is on the order of 170 kilometers per second. This is from their velocity field reconstruction. What I'm concerned about is not the what I'm concerned with, sorry, is not the local velocity field, but is something further away. But it is, of course, this local velocity field that causes our motion as well. And so our motion really is, our satellite's motion around the Earth going around the Sun going towards a certain direction within our galaxy, and so on and so forth. And all of these together added up give us the velocity that we think we see in the CMB, which is what the Planck collaboration in one of their last papers summarized in this table, where you see the relative velocities, some of which measured, some of which inferred, making certain assumptions. So the CMB dipole, just to summarize on something that you probably all know, has a temperature that is observed to be a temperature as it were to a co-moving observer times the dipole modulation. This is something that was figured out soon after it was observed, or in fact before it was observed, and then soon after it was observed by Stewart and Sharma and Peebles and Wilkinson. What you see is that this dipole modulation has an amplitude. The amplitude is beta, which is our velocity towards this rest frame of the CMB. So it is measured to be the temperature difference is measured such that we infer beta to be 1.23 times 10 to the minus 3 with very small error bars, so I don't even show them here. The same can be done in other observables. So what I'm looking at here is the number counts of galaxies in a flux limited catalog. And the number counts of galaxies in a flux limited catalog would be Doppler modulated as well, or would be modulated by such a kinematic boost as well. And again, you see a dipole to first order, and this dipole has an amplitude. The amplitude is proportional to beta, as we would expect, certainly by construction if we expand to linear order in beta. But it has an amplitude that is not 1, but it is 2 plus x times 1 plus alpha. And x and alpha are quantities I'll tell you about in a second. They're to do with the galaxy sample that we observe, with the galaxy sample that is cut in flux, and that is then observed on the sky in terms of its number density. So this is what we're going to look at for the rest of the talk. Okay, so I repeat here again, we're looking for a consistency check between the CMB rest frame and the rest frame of other high redshift sources, tracers of the density field. We expect these rest frames to be the same as it would be if we employ the FLRW metric. So going out, taking data, looking at what we get, and seeing that that the inferred velocities that lead to the anisotropies on the sky are different, that would mean a break of this consistency check, and seeing that they are consistent would mean that they're consistent. So, okay, I promise I'll explain a little bit what these two quantities are. This is a test that goes back to Ellis and Baldwin in 1984, when data wasn't really at the quality yet for us to undertake this test. But envisioning such data, we see a few effects. So what I show you on the left here is just a random distribution of sources on the sky. The first thing we learn in special relativity is, or one of the first things I suppose, is that we have this headlight effect. Angles are altered by a special relativity boost, and this leads to a clustering of the sources towards the direction in which we're moving. So the direction in which we're moving, I indicate here by this red point, and sources will cluster towards it. I exaggerate this here, leading to a dipole in the number density for boosted observer. That explains the factor of 2 here. X and alpha are to do with the sample itself. So we assume the sample to be just described by a cumulative distribution of number counts above a certain flux threshold that can be modeled locally as a power law. So this is this flux threshold to the power of -x. And in addition, we assume the sources to, in a certain observation band, to have a power law spectrum, where the power law spectrum in this band would be described by spectral index alpha. Using these two, you can see what would happen if we Doppler boost. The spectrum gets shifted to the right in the forward direction. The spectrum gets pushed up. So this is the Doppler boost. And for a observed flux of a source, it simply means that we collect more sources above our threshold. We gain sources in a flux limited threshold in the direction in which we're moving, and we lose sources in the opposite direction, which creates this dipole. Okay, so this seems particularly simple. It seems simple because all we have to do is we have to have a sample that is sufficiently well understood, and we can measure X and alpha, which we can do with, for example, the NVSS sample of radio sources, a sample that has been around for a while. Measuring X and alpha in these radio AGN returns a value of X of 1 and a value of alpha of about 0.75. So these two values together, including a prediction for beta, which we learned from the CMB because we want to do this consistency check, gives us a prediction of the kinematic matter dipole of this dipole in the number counts of galaxies that we would expect. So this lies at 4.6 times 10 to the minus 3. And because this was so simple, Blake and Wall in 2002 went out and took the sample and measured the dipole in the number counts they could find. So what they did is they modeled the sky as so, and they measure this parameter D, the dipole amplitude. What they find is, what I'll show you on the right here, they find a dipole. They find a dipole that points in the same direction as the temperature anisotropy in the CMB, so same direction as the CMB dipole, and they find it to be consistent with the standard model, with the standard interpretation of the cosmic background, which means this consistency test passed. And so what they found is they found an amplitude of 1.1 times 10 to the minus 2, which is formally higher than the prediction, but their larger error bars made it consistent, so their claim was justified. This, however, was revisited. This was revisited in the following years, in 2011 for the first time by Ashok Singhal, who I think is sitting here somewhere, here. Ashok's results were followed up in the following years. This is just a subset of the many papers I could show, where different radio samples confirmed indeed a larger dipole amplitude in the number counts of radio galaxies than expected. So this NVSS sample has been featured quite often, but here you see one of the pathfinders of SKA that has been taken up in this set of data. So the situation looks roughly like so, where we have a dipole that we see in the NVSS. This is a posterior on the dipole direction, which is sort of consistent with the CMB dipole, or it's actually very consistent with the CMB dipole. Here, just to show one other, I show the posterior of RAX, this pathfinder of SKA, with a direction that is only somewhat consistent. These are 95% confidence intervals. And you see down here that the posteriors of the dipole amplitudes in both these samples lie above the prediction that is down here. And so for a long time, all of these significances sort of danced around the 3 sigma significance level such that people just waited for more data. And more data is what we were able to provide, or at least what we were able to distill from a non-radio sample, from a mid-infrared sample collected by WISE in this CAT-WISE sample. And you see here that also in these mid-infrared sources, completely different sample, completely different systematics, we find a dipole that is too large compared with its expectation, here shown by the blue line, and a direction that is sort of consistent with the CMB dipole, but as was just said, about 40 degrees away. So this is something that we summarized recently in a review that is titled the same as the talk. So this is what I'm going to summarize. Okay, so just one slide on how we obtained our first results. We do the exact same as we did for the radio sample. We measure X, we measure alpha in our sample. This gives us a kinematic dipole prediction, such that we can now compare against this prediction with the dipole that we find in the data. And the dipole that we find in the data lies up here. Here I'll show you a frequentist result because this is what we did back then. And given that we did a frequentist test, we can actually assign a significance to this. So we found that at a p-value of 5 times 10 to the minus 7, none of the simulations that we undertook returned a value as high as the value that we found in the data. So this was very exciting. OK, so you'll have to take that as face value, or you ask me questions, which I'm happy to attend also at any point. Yes?
I just wanted to add the result that even from the aberration and effects on L greater than 1 on the CMB,
Yeah.
we showed that there's a 5 sigma consistency with the dipole. That also comes in.
Yeah, so you're referring to another consistency check which doesn't involve tracers like galaxies. It is a consistency check of CMB with CMB.
Yeah, but it is the aberrations of CMB, so it's not the L equal to 1. It's the higher multiples and the fact that they get correlated due to the Doppler shift.
That's right.
And what we showed is that measurement can be done to show that the result is consistent with the CMB dipole measured by just the L equal to 1 at 5 sigma. And a larger value, so we get an entire posterior, right? We give the posterior of the distribution.
Yeah.
So it's kind of, that also plays, what I'm saying is in this whole thing, that also would weigh on the other side, right?
Yes and no. So let me say 2 things about this. One is to maybe emphasize exactly what we're measuring here. And this actually refers to the slide. One is, are we moving with respect to the CMB with the same velocity as we're moving with respect to a sample of galaxies? That is one of the questions that this attempts to answer, but it is indistinguishable from the answer to the question, is there more matter in one direction of the universe than the other? So what we're measuring here is just a number count dipole, or dipole in the distribution of sources, which could occur apparently due to a boost with respect to the sample of sources, but could also be intrinsic to the sources or to any other effect. Right? So our results do not sort of nail down the kinematic interpretation. They could be that, but they don't need to. The second thing I want to say is that the aberration that we find in the CMB at higher multiples, the off-diagonal terms in the power spectrum, that is something that is a consistency check of the kinematic signal in the CMB. I'm not sure if that excludes any other explanation that would also give the same correlation in higher order multiples. If you had some sort of lensing signal on very large scales, that lensing might be able to give you a correlation just as well.
The way this is done is there's a model which you...
Oh, yes, yeah.
Right? So the point is, you can only ask, how likely is that?
Within that model, that's right.
Glenn will talk about it. But in the anomalies game, of course, we look for capital L equal to 1 effects. And we've also been careful in our analysis to leave the known L equal to 1 effect, which is some kind of a modulation of the amplitude of fluctuations on 2 angles. Beyond that, while there can be something, but there are 2 things that are involved here. There's modulation with a particular ratio of the modulation strength to the aberration strength, which also has to match for the results to be consistent.
Yeah, I agree.
So,
so there are many different consistency checks one could do. This is one, this would be another. We have to gather all the evidence. By the way, even though this looks like a summary slide, there's more, but I'm happy for a question nonetheless. Yeah, sure.
You mentioned some simulations in the previous slide.
Yes.
What are these? These are N-body
So these are not N-body simulations. These simulations were fairly simple. These simulations did not contain any clustering, but I'll talk about clustering in a second. So we would expect clustering in a local distribution, in any distribution of sources, especially if there is a contribution by local, very nearby sources.
Tested this on N-body. Your technique has been tested on standard N-body.
Not N-body. There's some approaches one can do. I'll show you one that talks about the clustering expected.
Sebastian,
yeah.
Can I also ask, can you show that the one that you show the direction? Yeah.
This one.
So, could you find some other ways? There is a big mask there, right? and finding a direction which is close to the mask. Not that you might have a best solution, because we didn't have. We tried to analyze on the, but this looks like an issue, right? There's a big mask there, and then finding the direction close to the area that there is no data.
I stopped thinking that it was an issue once we did comprehensive bias checks, and our estimators are not biased even if there's an input dipole that is below the mask.
I mean, you'd see that in your simulation.
Yeah, we would see that there. Yeah.
But can you rely on the direction?
Yes.
I mean, I can say that one can come. Maybe this I disagree. I can assume that based on the simulation, one can find that there might be violation of isotropy.
Yeah.
But then finding the direction correctly, I would be very doubtful.
Is that a question?
I don't know.
We should chat about it more, because I know of your paper, of course.
Yeah, so follow up on what Asim was mentioning and something that you mentioned. In the analysis that you were talking about, how do you account for the biasing of the quasar sample or radio sample that you're thinking about? Okay. And secondly, the WISE data is not very reliable in terms of redshift.
Okay.
What's the impact of the redshift errors on this inference?
Yeah, so I'll talk about your second question first, and then the first question is going to be on the next slide. So the second question about the redshift is that we're just integrating over all redshifts. So we're picking a sample of quasars that lie at high redshift, median redshift 1, and we don't care about the redshifts of the individual sources. We don't actually have them for most of the sources. We have them for a large subset of the sources, but not for every source individually. This Ellison-Boltzmann test, as it was devised back then, simply presumes an integration over all redshift, which is exactly what Subir referred to Jim Peebles having understood in the meeting last year.
Do you think messed up your K to L, like how do you define bias in that case?
Okay, so I'll show the next slide. Yeah, I'll show the next slide, and then we can talk more. Yeah. Okay, so the, second to the next slide. First slide is, okay, why is this result? This result might be due to, a vague number of survey systematics. There could be a clustering dipole, which is what your question referred to, that there would be contamination by low redshift sources, which have a stronger clustering, which is also maybe related to the bias. Biases in the estimation method, differences between frequentist and Bayesian estimators, frequentist estimators and Bayesian inference, or issues with the Ellison-Boltzmann formula in the definition of it. So there's a whole number of things that one could look at, and we have looked at them all, and I'm going to show you a subset of these. So this is what I wanted to show. The first thing to do as a cosmologist is, of course, to take a power spectrum and a two-point correlation of any signal you see on the sky. So this is our signal that we see on the sky. And computing the power spectrum shows us here at smaller scales power that can be described by a standard lambda CDM matter power spectrum. For the matter power spectrum, we of course need our redshift distribution and our bias. Because we're just integrating over redshift, we have one redshift kernel. It looks something like this. This is a redshift distribution obtained from a cross match of sources with SESS, where you see exactly that there is the peak lies at redshift 1. While we can't really distinguish different models of B being B of Z or B of K and Z, we simply assume a constant B to see if we can make it fit, and indeed we do. So this was just obtained with a fit that returns us a bias of 2 point something, which is indeed what would be expected for such a sample. And the fact that we can find a power spectrum that agrees with the data on small scales is really all we need to say this is what determines the clustering in our sample. And that determines the clustering in our sample not just at these smaller scales, but actually when extrapolated tells us what kind of fluctuation of the clustering we would expect at L equals 1, at the dipole scale. Right? So no, we're not doing n-body simulation. I don't know of any study who did full n-body simulations. There are some people here who did simulations with log normal codes. So this is relevant to explore. But already from the power spectrum here, we see that the accounting for the bias and accounting for the redshift distribution of the sources, we have a level of clustering that is expected that is much lower than the dipole that is measured all the way up here. Okay? So this is something that we can learn from here, and that addresses the clustering question that I had on the previous slide. A second thing that we can do, and I'll show you just 2 more slides on this, is we can investigate other low L power, which effectively might describe some sort of survey systematics that there might be in our sample. And we find upper bounds for L equals 2, 3, and 4, after which we run out of sort of, well, we already here find that the power is consistent with noise, so we don't even attempt to go up here, where we assume that it is consistent anyway. Here, well, 1 second. Here we find upper bounds for L equals 2 and L equals 3, which also tells us that the contamination by higher order multiples leaking into the measurement of the dipole would be low. So therefore, these are upper bounds. Yes, please.
Yeah, so can I know why you take this constant bias?
I take the constant bias because I want an easy life, but it's also, well, the one thing one could do is one could have a model of B of Z that goes up to is a polynomial in Z or so, and then you can fit for these, but it's not going to give a very different power spectrum. In fact, there was a paper by Prabhakar et al. That contained a fit to a second order polynomial, and the power spectrum, the theoretical power spectrum they get from it is very similar.
In that case, the redshift range was up to 3.5, right?
Can you say that again? Sorry.
Redshift range was up to 3.5, right?
They considered a maximum. You see that the redshift distribution dies out before, like.
And
before
they
4.
computed bias up to redshift range of 3.5, and
yes.
And that at 3.5, it was like bias was up to 9, right?
That might be, but in the computation, in the kernel of the angular matter power spectrum, you consider the multiplication of B of Z and N of Z, and if N of Z goes to 0, the bias can be 9. It doesn't matter.
But in your original paper, you took bias as 1, right? Now you're...
In our original paper, we did not do this computation.
Yeah.
We just investigated how large, roughly, the clustering dipole would be. Yeah. But this full angular power spectrum we only did here. Yeah.
Okay.
Yeah. Thanks. Okay. So here's L of 2, 3, and 4. I showed you before frequentist estimates of the significance of the dipole, such that it's only fair that I now show you a couple triangle plots that show you the posteriors on the parameters in a Bayesian inference. The Bayesian inference allows us to do many things. It allows us to explore different likelihoods. It allows us to explore, therefore, different clustering or different noise models for the data. Something that we did here, which I'm not going to go into unless you ask me about it, is we considered a Poisson likelihood and a generalized Poisson likelihood. In fact, the generalized Poisson likelihood is very much preferred. That simply derives that the data is over-dispersed with respect to a Poisson distribution. This is one example of the many things one can do. The point is that in these posteriors, you see the posterior on the dipole amplitude, and that regardless of in this case, of the 2 likelihoods considered, just remains at the value that we had before, and it remains discrepant with this vertical line here, which is the expectation. So the anomaly of the dipole is robust with respect to exchange of noise models. The dipole anomaly can also be investigated in terms of these higher order multiples. And so because we have an even mass, there might be a coupling of odd multiples, or multiples that are 2 apart in L. So the next higher multiple that might be thought of an issue is the octupole here. So here we considered a simultaneous fit of dipole and octupole together. What we find is that an octupole is sort of, it peaks at above 0, but it's sort of consistent with 0. Nevertheless, the dipole amplitude remains anomalous, just as before, which then here allows the statement that our measurements in this data set are robust with respect to systematics that might appear at higher multiples as those investigated here. What you also see is a slight positive correlation as opposed to a negative correlation that would be worrisome. So in this case, the dipole amplitude actually becomes slightly larger, if anything, when considering an octupole. Okay, so this was all about the mid-infrared data. Back to the radio data, there was a paper just about a month ago or 2, we have December, so 2.5 months ago, by Lucas Burma et al., who investigated a number of radio samples simultaneously. So they looked at NVSS and RACs, as I showed you before, but they also took into account LOFA data that offers a very high number density. Thank you. And what they found is that all of these radio results return dipoles that are too large with respect to their expectation. In fact, they claim that they lie 3 to 4 times higher than the expectation, whereas what we found is 2 to 2.5 times larger. I mean, this is interesting. First, because the radio dipole anomaly, as Ashok Singhal found, now it does seem confirmed with even the newest data, not just the old NVSS data. But in contrast, or well, taken together with the results that we found in the mid-infrared, again, these are 2 very different types of observations: ground-based, space-based, of course, satellite and dishes on the ground. These are various radio catalogs, all of which find the same result. These are distinct sources, astrophysically and actually physically distinct samples of sources, and they all return this value that things are a bit too large. So where to go from here? Yes?
What are the number of sources that were actually present in this home paper?
Yeah, thanks. So the numbers of sources in our mid-infrared sample are 1.6 million. The numbers of sources in the radio samples, it depends a little bit on how strongly you cut on the flux. Okay. NVSS had about 400,000 sources. RAX had about 400,000 sources. I think LOTSS returned, I think, just below 300,000 sources.
Wouldn't that have much higher short noise, right? Because the number of sources are less.
The number of sources respectively is lower, which means higher short noise per sample. But if you take the samples together, you suppress the short noise. Okay. Yeah. Yeah. The direction is compatible with infrared as much as I showed you on the picture before, at least. So, okay. So the radio samples have directions that are slightly, you know, the 2 green ones. This is, I don't have LOTSS on here. I believe it's in the same direction as well. We can, okay, I don't know if we can do a coordinate transformation in our head, but I think this is in right ascension and declination, yes. So where are we? Declination lies at around -6 in the mid-infrared, so that should be compatible with this. And right ascension, I think, lies a bit to here in the mid-infrared. Again, LOTSS alone is not shown here, but roughly consistent, yes. Yeah, thanks. Okay, so where to go from here? We have 2 very distinct samples of sources, both of very high significance. We need an explanation. Sadly, in contrast to the other anomaly Naiman mentioned today in the birefringence, where we have a model, we don't really have a model here. So the best thing we can do is we can just gather more data. And there is more data coming up. So the first thing I want to address is maybe a redshift dependence in these results, which will be possible to investigate in future data sets. So this requires a bit of formalism, which I'll get to by a slight detour to address the last point in the list of possible issues that I mentioned. So Ellis and Baldwin formulated this test with samples that have been integrated over redshift, where we don't care about redshift information. Some years ago, Martins and collaborators looked at a redshift-dependent expression for this kinematic matter dipole, which you see here is dependent on factors that you can actually only compute within a given model. So they computed this in a Friedman model. So the question here is, can we relate this expression to this? Do they really describe the same thing, or is one of those 2 formulations wrong? So the first step that was done in this regard was done by Nadolny et al., then a student of Ruth Durer, who translated the Martins et al. Expression into one that actually shares at least some of the terms that appear here. And what one finds is that one can then relate the right-hand side formula to the left-hand side, but only after answering a question that was posed. So maybe some of you have read this paper where they considered line-of-sight dependent effects and wondered whether they could affect the formula that Ellis and Baldwin wrote. And the answer to this question, are the observed quantities enough to predict the dipole correctly? Yes, they are, and you can read my paper if you want to. But just for now, the formula that I showed you before has a term down here, where the term integrates to -1 if we integrate over all redshifts. And it therefore returns this formula, and these redshift-dependent terms integrate to give us the observed terms that here I list under the same name. Okay, so what if we don't integrate over all redshifts? If we have a survey with redshifts, we can basically cut on redshifts. We can do redshift tomography of the kinematic matter dipole, which people have been wanting to do for long. If we do that, we have to consider the fact that redshifts are boosted as well, obviously. And if they're boosted in different directions than a forward direction and a backward direction, such that if we select a sample of sources as indicated by the blue here, we might lose or gain sources depending on whether they're in the forward direction or backward direction. So this leads to an expression of the Ellison-Baldwin formula that we worked out last year that has a correction term. So you get basically what Ellison-Baldwin wrote before, plus a correction term that I'll call a boundary term, because if you consider a top hat, it really is a boundary. And this boundary term is going to be essential to be computed with future surveys that have redshifts, among others the SKA. This can be done also with photometric redshift kernels, in which case the boundary term just looks a bit different. This is just a forecast that we did for the SKA back then, considering different redshift distributions that the SKA might gather, and we find boundary terms that, dependent on the redshift, on the effective redshift of the respective redshift bin, can give values that are substantial compared to the Ellison-Baldwin terms. This only happens if we cut on redshift. In everything I showed you thus far, we did not cut on redshift, so these terms don't have to be respected. So this is quite exciting now in the work of SKA that I'm involved in, where first of all we noticed that the redshift distributions that we considered here are superseded by the newest redshift, the newest radio measurements that found that we actually underestimated the number of star-forming galaxies in these samples, which appear particularly low redshift. Because they appear low redshift, we have more clustering than we expect, which means the clustering has to be removed before considering the kinematic contribution, which means we have to cut out those sources, such that if we have redshift, cut out the sources, we get to the kinematic signal, but we have to respect the boundary term here as well. So this will become essential with surveys like SKA. Okay, and then maybe just to stop, in finding an effective description of what this kinematic matter dipole might be, one could wonder, is it just kinematic? Like Tarun said, we have more evidence that things might just be kinematic in the CMB, then we have a clear expectation of what it should be here. What is the rest, right? If the axis of the matter dipole is not just kinematic. What we considered here was a model that is based on the fact that the kinematic matter dipole expectation in the radio and in the emitter infrared is different. Because it is different, we might have a handle on a model where we assume that the residual dipole that might be in both, this axis of dipole that might be in both, is constant. And of course, we find a degeneracy of the kinematic contribution and a residual contribution that gives you a line of degeneracy as shown here. What we find is that we actually have slight evidence for a model that has a kinematic matter dipole in both the radio and mid-infrared that lies at a value that's close to expected. But that just means that we have to trade it off for this unusually large excess dipole, which in and of itself breaks the assumptions that we have in lambda CDM, where we don't expect a clustering dipole that is so much larger. Right? So we found, we evaluated the Bayesian evidence for this model and computed the Bayes factor, according to which it is somewhat significant. But really what we need is more data with which we can do these tests up until we have theoretical models that we can entertain as well. And there are some theoretical models based on the work by Mike Turner in the 90s, Guillaume Dominic et al. With Subodh and Subir, who are here, worked out a model where isocurvature perturbations of horizon size can, produce a discrepancy between the CMB dipole and the matter dipole. Okay, I'll leave you with a slide and the summary that Ellison-Baldwin wrote in their paper, where they wrote that if there is a serious disagreement between the CMB dipole and the matter dipole, then we would have to abandon one of these three or more facts. And one of these three facts is that the standard Friedman-Robertson-Walker universe models hold. So this is quite a significant test. The results appear to be quite significant, and the implications appear to be quite significant. We just have to figure out what they are. Future data, SKA, Euclid, especially SPHEREx, which will follow up on the mid-infrared results, hopefully will shed some light on this anomaly, and then I'll be happy to take questions until then.
you want to start from?
What's the main bottleneck in using n-body to test of the techniques? Is it the lack of large enough volume simulations, small enough mass?
No, there's no big bottleneck. You could use n-body simulations if you have some sort of halo model. You populate the n-body simulation with the properties you believe you learned from your data. Sure.
I wonder, because unless I misunderstood something, when you extract your signal for dekinetic, you already impose the model that this is due to a Doppler boost.
No.
Is that correct?
No,
From the data.
Yeah. No, the motivation to do this test comes from Doppler boost. The model is just what I showed you at the very start. Where is it? Here. The model is just this, that we have a number density of sources on the sky in a flux limiter catalog, and we modeled it as a monopole plus a dipole modulation plus potentially higher order multipoles or selection functions or so.
This D is the number that you extract from?
D is the number that we extract. There is a prediction for that number if we were to assume a kinematic interpretation, but this doesn't assume that kinematic interpretation. Yeah.
Thanks for the nice talks, very, very interesting. If we go to the more prosaic interpretation, which would be a measurement systematic, have you looked at the effect of source blending, for example? I'm thinking particularly for radio sources, you could imagine that that would change your, that power law behavior for the what you call the magnification bias could be affected by blending and deblending as you increase the flux of the sources. Did you look at this?
So the blending and deblending. Okay, so you're saying there would be a.
So if you have two sources very close together and they are faint, you would call them at one, count them at one as one, and then within your resolution element, and as they become brighter and brighter due to the dipoles, for example, they would be counted as two. They would be detected as two, and then they counted. That would change. I don't think it would look like a power law, a usual magnification effect. I mean, the reason I'm saying this is because in weak lensing, when we do cosmic magnification, we worry about these things, and this is also very small effects. Yeah.
So two things happen. One is that the counting statistics are changed, right? So first of all, you sample your Poisson, you sample your sources as Poisson from an underlying density field, such that over the sky you already have super Poissonian noise, but this double counting of sources would increase that over dispersion even more. This is something that we check with this generalized Poisson. We also check a negative binomial distribution. These are the same classes.
So you looked at the statistic in different direction, and it seems okay.
We also did that. That seems okay. Well, the statistics in different directions of the one-point distribution is exactly modeled by this dipole, but the statistics of the width of that one-point distribution is consistent with this. Yes. Okay. The second effect, which is to do with the fluxes, I would expect this to happen mostly for bright sources. You would expect them to have this. At
your detection limit, you could count them as one or two depending on your.
Yeah, exactly.
And a small increase in the flux from time to time, you would.
I don't think I have this figure here.
You would deblend them.
But we did a check where we actually scanned through the sample at different flux cuts, and all of the different flux cuts return a dipole that is basically at the same value.
All right. Okay.
If I don't have it here, I'll show it to you later. No, I don't have it here. I'll show it to you later.
But that's,
yeah, thanks for your question.
Thanks for the nice talk. Sorry, it's me.
Oh,
Hi, Sebastian. A comment and a question. So the comment or question to you is relates, in fact, to what Subir shown this morning, that plot of looking at the past light cone using a more general approach than assuming a Robertson-Walker-Brown plus perturbation. Also, I think this is also related to what Dick Bond referred to as HIJ. So to look at using what Roy Martins called a covariant approach. So have you looked at that recent piece of work using this, what they call covariant model-independent approach? So that's the question, one question. And the second is, there is a recent paper by Pedro Ferreira and collaborators using some Bianchi models.
Yeah.
Can you, if you know that, if you can comment?
Sure.
Thank you.
So about the first question, the covariant approach that Roy Martins developed, and also some other people in the field, this approach is mostly to model low redshift phenomena. It's a cosmographic approach at low redshifts. So this doesn't apply here because we're looking at large redshifts. Sorry? It won't apply, no. To the degree that this general relativistic approach applies here is what I addressed in the slide that showed the results by Roy. Yeah, here. So this formula, when integrated over redshift, returns this, but this is derived in their formalism. So these things are consistent. The second question you had about the paper by Alethea Martin and collaborators, they considered a anisotropic model as an example of Bianchi 5 model, where they then modeled in different ways, but among others, a bulk flow in the energy momentum tensor. And they saw that this bulk flow in the energy momentum tensor corresponds to the curvature that exists in that particular Bianchi model, right? And then they wanted to see whether this bulk flow can create a difference in the rest frames between the CMB and at late redshift, at low redshift, the matter. And they found that none of these models really work because they all, due to the curvature, induce a huge cosmic shear, which you can constrain with CMB, right? So you can constrain it with the ISW effect, or sorry, with just the Sachs-Wolf effect, and you can constrain it by looking at CMB polarization. These constraints on shear therefore exclude most of the Bianchi models, because most of the Bianchi models start anisotropic and become isotropic. There are some models, the Kantowski-Sachs model, for example, that starts isotropic and becomes anisotropic. So there the shear constraints apply. Yeah, so there the shear constraints apply differently. But all of these models, attempt to create this bulk flow that refers to the kinematic interpretation. It's an attempt. I think it's interesting work. It's interesting to see that it doesn't work because it constrains this type of models that might be able to explain this work.
I guess you refer to the CMB constraints that were done a few years ago.
Yeah,
by, what do I remember?
Sade et al.
Yeah, Sade, yeah,
I mean,
Daniel Sade, yeah. So Bianchi 9
so
is not part of what they used, and I think it's worth trying because it's the most general.
They only tried a subset of the Bianchi models, yes. But those Bianchi models with shear are the problematic ones, which are mostly.
In the interest of time, one
last question.
Okay.
Thanks for your question.
Okay, so when you are constraining the dipole in addition by adding the octopole, I noticed that your posterior is broadening on the higher dipole side, right? So is that simply explained by the generalized Poissonian distribution, that the likelihood that you are taking? Or what is the way to understand that? This one, yeah. Next.
Yeah, so the generalized Poisson likelihood increases the width a little bit on the posterior.
Both sides.
Sorry?
It
on both sides?
Yeah.
The octopole increases the width on the posterior, not due to the generalized Poisson, not to the overdispersion, but due to the correlation that the dipole has with the octopole.
I see.
There, it is mostly on the sort of side that is away from the expectation, not the other one. So I assume you're asking in the context of the significance that the dipole, so basically at which significance does this posterior disagree with the expectation, or conversely, at which significance does the measurement of a dipole in an estimator disagree with a set of simulations.
Yeah.
And so for this, I can hopefully show, maybe I have that one. Let's see. Another slide, here it is, where we do just this. So here you consider a ensemble of simulations that contain a dipole and an octopole of the level that I inferred before, and compare to it the measurement of the dipole that you would make, and then you can evaluate its significance. If you just fit with a dipole only, which would be inapt because you know that you have an octopole in the data, then you find the significance reduces.
Yes.
But what you better do is you fit for a dipole and an octopole at the same time, even in your frequentist method, and that brings these distributions to be very close to where they were before. So the significance would still lie at roughly the same value. Thanks.
Okay, let's thank Sebastian once again.
See, he knew what the answer is. That's all. We're done. So it's great to be here. Thank you for inviting me, even if it's to tell you things that maybe you know. But we've decided we need to tell people over and over again because they tend to forget about this. Because it's not that the data has changed that much; it's that the data hasn't changed, and we keep seeing this. Now, when I was invited to give this talk, actually Andrew Jaffe was supposed to come, and the two of us, looked at each other and said, "Okay, who's going to talk about statistical isotropy and who's going to talk about topology?" And we decided that Andrew would talk about topology, but unfortunately Andrew can't be here. So I may say something very little about topology because that's mostly what we've been working on over the last couple of years, but a little bit off about this. Okay, so just to remind people where Case Western Reserve University is, it sits here in Cleveland, which is due west of New York. It also happens to be the place where the Taurus balloon mission is based these days because of NASA's silly behavior these days. Is this going to change? Nope. Okay. You may have heard of the Michelson-Morley experiment. It was done at Case Western back in the 1980s. So we have been doing physics there for a while. And because of that, John D. Rockefeller built us a building. So come visit the building. It's a very nice place. It's also the home right there to the Cleveland Orchestra, one of the best orchestras in the world, and the Cleveland Museum of Art. And this building sits right about here. Okay? And if you like rock and roll music instead of classical music, it's also the home to the Rock and Roll Hall of Fame. So lots to do there, and you should come visit us. And in tribute to another person who died recently, Frank Gehry, one of his buildings sits on our campus. Okay, so this is work that I've been doing with a lot of people over a lot of years. And currently, a bunch of us are put together a collaboration called Compact. And we're all over the place, and any of us would be happy to tell you about the work we're doing. And the T here has to do with topology, and the A has to do with anomalies. And so those are the two things we mostly are thinking about. All right, so let me get to the meat of the talk. For a long time, since we've been able to see anisotropies over the whole sky, and since we've been making really high-quality maps of those, even ones where we try to take out the galaxy, and even better maps, if not over the full sky, what we've been told to do is that we're supposed to expand our sky in spherical harmonics, and that it's the coefficients of those spherical harmonics that are the interesting things. And why is that? Well, it's because in cosmology kindergarten, we're told that the sky is statistically isotropic, and those ALMs are independent, nearly Gaussian random variables, where the nearly, we haven't seen any deviation from the nearly at the primordial level. And so what we're really trying to do is we're trying to find, these are independents, and so we're just trying to find the variance of the individual ALMs, and those are the angular power spectrum, and all of the interesting information, pretty much is contained in this angular power spectrum. And so if you can measure that, you know a huge amount of what you want to know as a cosmologist about the universe. Okay? And this is closely related to this principle that we've been talking about, that the cosmological principle, that the universe is homogeneous and isotropic, at least statistically. And we have good evidence for that, we've been told, because if we look up at the sky, then we see something that looks awfully homogeneous and isotropic. Well, of course, it doesn't look homogeneous because we're sitting in one place, but it does seem to look isotropic. What has the cosmological principle ever done for us? Well, an enormous amount. It's really what's let us do cosmology in many ways. It's allowed for a vast simplification of the Einstein equations, where instead of 10 coupled second-order nonlinear PDEs that we struggle to solve numerically, we are able to reduce it to just a couple of Friedmann equations for the background. It allows us to expand or organize perturbations and representations of the rotational symmetry. In other words, do an SVT decomposition, which is what really lets us do everything we do. It allows us to analyze key non-equilibrium homogeneous processes in a cooling universe, like nucleosynthesis or recombination, right? And it allows us to replace sample averages. So it allows us to let sample averages, taken over different directions, to stand in for ensemble averages of statistical quantities, which is what our theories really predict. Okay? So without that, we would have been in many ways lost. And so it's a big thing to give up. Right? And so giving it up requires us to really be confident that, that we should. And what I want to convince you is that there's a lot of evidence that by the standards of, that by the standard of evidence that we usually impose, even in fields where it's more justified, we're there, right? And so either we have to come up with some explanation, and we don't seem to have any other one other than our cosmology doesn't support the cosmological principle. So of course, now this is of course quite an old slide, but a pretty good one showing the amazing success that this, that this picture of the universe has afforded us, where to hundreds of points, right, in very, very complicated curves, we can fit them with 6 or 7, depending on how you feel that day, parameters. And that's really an astonishing, of course, experimental achievement more than anything else. Thank you, Lyman. Right? But also in a remarkable agreement with theory, and that's what makes us so excited that maybe it's right. Right? Because it really has done a really incredible job, as Dick told us. Okay? But shouldn't we check that this assumption really is true? Because, as we said, everything we've done has relied on that assumption. And when we write down likelihood functions, we build the assumption into the likelihood function. When we analyze our data, not always, but in most cases, we have built in this assumption that the CLs are independent of one another, that the ALMs are independent of one another. So I'll tell you about just a few of the troubles in this isotropical paradise. At the bottom line, I want to convince you that there's more than what we'll call 5 sigma evidence against Gaussian random statistical isotropic realization of lambda CDM in ways that seem to demand that the statistical anisotropy part of that GRSI is violated. And I will finish off with just a little promise of topology musings in Andrew's absence. And you feel free to ask me about those in the imaginary time at the end of my talk. So let's go back to Kobe, long time ago, 30 years ago. I think this is the first paper, and people who were more aware back then of what was going on can correct me, but I think this was the first paper that said, hey, there's something wrong at low L. So Andy Gould, way back then, said, hey, the quadrupole just is lower than it's supposed to be. Okay. Now, really, it took a long time for them to say anything about it, but the Kobe people didn't just calculate the angular power spectrum. Now, I think when they went and proposed Kobe, they would have told you that one of the things they were going to measure was the angular correlation function, because at the time, astronomers were interested in angular correlation functions, but by the time it came time to publish papers with results, astronomers, cosmologists had become much more interested in the angular power spectrum because we had theories that told us that that was what was interesting. And so it was not till the 4th year data release that they produced this paper about the 2-point correlations in the Kobe DMR anisotropy maps. And they didn't even in the papers say why these were weird. You're shaking your head, Dick. Oh.
We knew all about this from the very beginning.
Yeah, but this was the first time it was published, as far as I know, and as far anyway. Okay. If there's an older paper, that's great. I think this is the first paper where they published it. All right?
It doesn't matter what they do, it's what I do.
Okay. As we said, people noticed nevertheless. It's interesting that no one wrote down a statistic saying why this was odd, right? And nothing in this figure shows why it's odd, and there's nothing in the paper that says it's odd. But people noticed that there was something odd about this. Okay. So what was odd about this? Okay. So as I said, the first hint was that the quadrupole was low, okay, even though the other C sub L's were not low. And really, you should not think of this as a low L anomaly, but as a large angle anomaly. Right? And what's really interesting is not the fact that the quadrupole is low, but that there's something funny about the angular correlation function. Now you might think, well, why do I have to look at the angular correlation function since it has all the same information as the angular power spectrum? And the answer is we do this all the time, right? We take transforms of data and signals jump out at us. And so what's interesting here, and here's from the third year of WMAP, where this becomes very clear, but you can see the exact same thing as that was happening in those COBE maps, is that in every single band that's dominated by the CMB, Q, V, and W, the angular correlation function seems to be very small compared to what the theoretical prediction. Okay? So it's not that the angular correlation function differs from the predicted angular correlation function. It does, but not very significantly. Depending what norm you use, it'll differ at a p-value of 0.1 or something like that. But it is very close to 0 in all three of the measured bands outside the galaxy. On the reconstructed full sky map, outside some reasonable mass of the galaxy. But somehow not when you took the reported C sub L's and turned those into an angular correlation function, then you got the green dashed lines, or if you took the full sky reconstructed map and took the angular correlation function measured directly, it agreed with this maximum likelihood estimate of the CLs, which seemed to have a little bit more angular correlation than everything that you'd measured and actually trusted. So they put a statistic on that called S1/2, which just says integrate C of theta squared, d cos theta from 60 degrees to 180 degrees. Turns out not to matter very much exactly what you do. This isn't optimized. It isn't cherry-picked. It isn't fiddled with. It's just kind of something simple you would write down, and pretty much everything else gives something very close to that. Okay? And how unlikely is it? Well, it persisted all the way through WMAP that if you looked at the full sky, S1/2, it was small. It's supposed to be about 50,000 micro K to the fourth. Turns out on the full sky to be about 8,600 micro K to the fourth. But if you look outside some reasonable galaxy map, it's about between 11 and 1,200 micro K to the fourth, which happens accidentally a few times in every 10,000. So where is the difference between those? Well, it must be between that full sky result of 8,600 and the cut sky result of 11 or 1,200. It's in pairs of points, at least one of which is inside the galaxy maps. Okay? And by the way, that hasn't changed when people have gone and reconstructed, said they've done a better job reconstructing the sky close to the galaxy. Somehow, if you want to believe that that's really cosmology, it just happened to sit behind the galaxy. There's very little angular correlation outside the galaxy, and it doesn't really matter exactly what mask you take. And there's more correlation if you take pairs of points, at least one of which is inside your mask. I think we mostly expected, probably wrongly, that this would go away in Planck, and it didn't. Okay? So you see essentially exactly the same thing. So somewhere between, actually the 0.1% is probably wrong. This has to do with how Planck reported things. They never reported p-values really that were less than 1 in 1,000 because of how many full focal plane noise maps they had. So somewhere around 3 out of every 10,000 realizations of the concordance model of inflationary lambda CM have so little cut sky large angle correlations. And most of those look nothing like the sky, because there are two ways to get a low angular correlation function. One of them would be to have all of the low L C sub L's fluctuate down. After all, if C sub L's were all 0, then the angular correlation function would be 0, and S1/2 would be 0, and that would do it. But that's not how the sky does it. The sky does it, actually, by having almost exactly the right quadrupole to cancel the contributions of the higher L multipoles. And that's not quite true of 2 and 3. It's not quite as low as you could get to cancel the others, but it's pretty good, etc., up to about C sub 6. Okay? So to obtain the value of S1/2 that we see with the observed higher L C sub L's requires kind of tuning to C2, 3, 4, and 5 to agree with one another. In other words, it's kind of a conspiracy, and that's really hard to do if you're going to try to change the inflaton potential, because even if we replaced all the theoretical CLs by their measured values up to L of 20, cosmic variance would only give us about a 3% chance of recovering so little correlation in a particular realization. Okay? Because of cosmic variance spoils the smallness of S1/2 because it's quadratic in the C sub L's. So how do you understand this? Well, one thing you say, I never believe a posteriori statistics. Now, in particular for S1/2, this is a little difficult because, as Dick said, we noticed this in COBE, and the problem got about 200 times worse by the time you did the WMAP measurement. Now, if you go back and take the COBE errors on this, it was about a p-value of about 0.5 or so, and it went down to about a few times 10 to the minus 4. I never believe anything less than 5 sigma. Well, we'll get there. But if you want to actually explain this, you're going to need new physics that correlates the C sub L's, and therefore that correlates the ALMs.
Sorry, Glenn.
Yeah.
It seems to me you're just saying that the 4-point function is smaller than what you predict from a 2-point function. Saying that
it's this very particular 4-point function is much smaller than you would predict. Well, there's two things. It's much smaller than you would predict from just having a diagonal correlation matrix.
From Wick theorem, basically. So for Gaussian fields, 4-point function is a product of 2-point functions, and you're saying it's much smaller than that, right?
But it's also smaller in such a way. It's not smaller because the CLs have all fluctuated downwards. It's smaller in such a way that seems that the C sub L's of different L are actually canceling one another, their contributions. Because S1/2 isn't a sum over CL squared. It has off diagonal.
Is a 4-point function.
It's a particular 4-point function.
I'm saying that's much lower than what's predicted. That's all you say.
There's a particular 4-point function,
right?
S1/2. So that's very small.
So I'm just saying that it's anisotropic is kind of, there's a perfect degeneracy between non-Gaussianity and anisotropy, and you take a fork there, which you didn't have to.
I'm saying that in order to get the angular correlation function to be small in the way you want, that 4-point function to be small, it doesn't do it in a way that the C sub L's, if you like, they could be Gaussian with non-zero mean, for example. Mm-hmm. Okay?
Yep.
So the C sub L's could be Gaussian with non-zero mean, for example, around some model.
You're not disagreeing with me, are you?
In that sense, in other words, I'm saying that you can't have that's saying that the C sub L's are correlated with one another.
Yes.
Yes.
So that's the
The point is that the C sub L's are correlated with one another. Okay. And you don't get that in a statistically isotropic model.
You could get an isotropic but non-Gaussian universe. I'm going to leave it at that.
Are there other ways in which we should, so having seen that statistical isotropy or Gaussianity in some very odd way is being violated, people have gone off and looked at many, many, many different things. And I'm just going to pick a few of them. And I would say I'm going to pick them because they're things that we've worked on. That's not completely true. Actually, I'm going to pick them because Dragan Hutter chose these ones to look at, and so I'm going to follow up on his choice. Okay. So the first one is alignments. Right. So if we see birds flying in the sky like this, we don't say, "Oh, what a funny accident that they all happen to be lined up like that." We say that there must be some physics behind it. So how can we do such a thing? How can we look for alignment of directions of multipoles of our ALMs. The ALMs are not very convenient for that. A different representation of data on the sphere turns out to be very useful, called multiple vectors. We're used to multiple vectors for the dipole. We would probably, if you asked me what the dipole is of the CMB, I wouldn't tell you what A11, A10, and A1 minus 1 are. I would tell you the amplitude of the dipole and its direction. Right? Similarly, for higher L's, for L equals 2, I could tell you 2 unit vectors and an amplitude. For L equals 3, I could tell you 3 unit vectors and amplitude. And those unit vectors and that amplitude turn out to be vectors and a scalar, or pseudo-vectors and a scalar. And so they transform in all the usual ways that vectors and scalars do under rotation. So they're kind of easy to understand in that way. And they're convenient for certain things and not for others. We were very happy when we thought we invented them, but it turns out that you can write them in a much nicer way as the product of L directional derivatives on the unit sphere of 1 over r. They were used by this fellow in this kind of vaguely known book, treatise a long time ago. And it turns out that in certain corners of physics, like geometrology, apparently they still use this. Okay, so in this representation, you can think of the quadrupole as having 2 vectors. You think of it as a plane. The octupole as having 3 vectors, or 3 planes. And suggest defining the area vectors just to show you on a sky. So here they are. The vectors associated with L equals, the vector associated with the plane of L equals 2 is this kind of dark gray, and the 3 vectors associated with L equals 3 are these dark black. They're also up here in the north, but they're easier to see down here in the south. And notice that they're all clustered here in one small bit of the sky, which suggests, first of all, that L equals 2 and L equals 3 aren't uncorrelated with one another. And second of all, now it turns out that the multiple vectors of a given L aren't randomly distributed on the sky, but they're much more widely distributed than these 3 are. Okay? And so it is very unlikely that the 4 planes of the L equals 2 and L equals 3 would be sitting so close to one another on one little part of the sky. And it turns out that closeness, you see how the quadrupole plane is sitting right at the center of the 3 octupole planes. That turns out to become about, if I remember correctly, about 5 to 10 times more significant when you remember that you're supposed to subtract the Doppler quadrupole, or correct for the Doppler effect in the quadrupole. Okay. So the p-value of that alignment is somewhere around 0.1%, or in some unusual, there are many different foreground subtracted maps, 0.6%. Because to measure this well, you have to use a full sky foreground subtracted map. Okay. Another one that people have talked about already today is often called dipole modulation. Some people will talk about power asymmetry. We tend to talk about low northern variance, and that's because, well, here you can actually see it just with the naked eye. If you squint at this map, I think you'll agree that there's more variance down here than up here. Okay? And here's showing that exactly. So if you look at the PDF of variance on the sky, here it is for here's the probability distribution function that you would get. Here's the value in the south, which is absurdly normal, and here's the value on the north, which is sitting way down here at one part, a p-value of 0.001. Okay? So the north really does have much lower variance than the south. Okay? And of course, we can write that as dipole modulation, but you would tend to think of dipole modulation as lowering the north and raising the south. Okay? And that's not actually what we see. Okay. The parity anomaly, well, if you look at, at the C sub L's of low L, here we go, L equals 2, go up to 3, 4, 5 is higher. Sorry. Let me get this right. Okay. Yeah. 2, 3 is higher, 4, 5 is higher. I got this wrong. Sorry. This is, 2, 3 is higher, 4, 5 is higher, 6, 7 is higher, 8, 9 is higher, 10, 11 is higher, 12, 13 is higher, 14, 15 is higher, 16, 17 is higher, 18, 19 is higher, 20, oops, you have to go down to 21. So the first 9 pairs of C sub L's C sub 2L plus 1 is bigger than C sub 2L. Okay? There are others. I'm going to skip them because I only have 10 real minutes left. Okay. So with so many anomalies, what should we do? Well, we're trying to write a report, a review of them. But to be fair to all of our colleagues, there are over 2,000 papers now on anomalies, so it's a little bit hard to write a review, so we're a little bit behind. So what we did is we followed up on some work by Dragan Hutter and Jessica Muir and Adhikari a few years ago, in which they picked out those 4 anomalies among all the other anomalies, and they asked, well, are they correlated? Okay. And the answer was, a little bit. The S1/2 anomaly and the low northern variance are a little bit correlated. But they didn't ask quite the right question, because the real question is not, are those statistics correlated? Because, of course, that they were looking at the peaks of the statistics. What you really want to know is, are the tails of those statistics correlated? And so we went out and looked. So here are the in 4 different Planck foreground subtracted maps. Here are the values of those, the p-values of those statistics along the diagonal. Okay, and here are the pairwise values that we got. Okay, and here is how much bigger those are than just multiplying the p-values. Okay, so if these were all completely independent, we should just be able to take the product of all those 4 p-values, and we get some number like what, 10 to the minus 3, 10 to the minus 5, 10 to the minus 11 times some number like 20. Okay, so, and that's so some very small number. And the answer is, well, it turns out that S1/2 and sigma 16, so lack of large angle correlation and low northern variance, are somewhat correlated, but not enough to make up for the for the fact that having both of them is still considerably less likely than having either of them. Okay? And so if you look at how many out of we produced 10 to the 8 realizations of noise-free lambda CDM, and we got 3 of them were as anomalous as Commander in all 4, none of the NILC, 18 of the 7, which is always the least anomalous in all the anomalies, and 1 in SMECA. Okay? So the answer was they were weakly correlated. These numbers are about 50 times what you'd get if you just multiplied all the p-values, but they're much, much smaller than the minimum of the 4 p-values, which is the worst it could have been. Okay? So that would falsify statistical isotropy at 5 sigma and TT correlations. Okay? Now you could say, well, did you just cherry pick those statistics? Well, there are a lot of other statistics I didn't write down. Okay? And some of them are going to be obviously uncorrelated. We'll get to that in a minute. So here are the 2 comments that I've heard. You can't believe data without a model. So I haven't given you a model for this, and until you give me a model, I can't believe what you're saying. Now, anyone who believes that didn't believe in the perihelion precession of Mercury from 1848 until 1915, still doesn't believe in high TC superconductors. A lot of times we discover things as frequentists, and then we explain them as Bayesians. Okay? So discovery often doesn't happens before we have a model, and then we have to explain the data. We don't get to find the model and then find the data. Now, of course, you should worry about look elsewhere penalties, but part of the reason that, of course, that we demand 5 sigma is because we worry about look elsewhere penalties. Okay? That's a big part of it. So also, you should balance look elsewhere penalties against what I'll call look more closely rewards. Okay? So for example, in the S1/2, I talked about the p-value of 10 to the minus 3 for S1/2 and TT, but I didn't tell you about the 10 to the minus 3 p-value for S1/2 of EE. Now we don't really, I didn't talk about it because it's not clear that we trust S1/2 of EE from Planck, but I can point you to the paper by well-respected colleagues of ours reporting on S1/2 of EE, and I know the referee, and he's not here to talk about topology, and he let the paper get published. So it's out there, another 10 to the minus 3, and if you ask what's its correlation with the S1/2 of TT, it's very low. Okay, so if you want to tell me that I probably have a factor of.
Can you just tell me the sign of what you just said? Are you saying that you don't believe this paper?
No, I'm saying I don't know if I should believe this paper, but it is in the data currently, right? I didn't include it in my evaluation of the p-value.
Anybody try and reproduce it? I mean, it's a very difficult regime to get the answer. But
Yeah, I mean, you mean have people redone the Planck analysis?
For example, this large team that you asked.
No, we have not tried to analyze the EMO data of Planck. Yeah, because I'm not sure it's worth it. I mean, we should reanalyze the EMO data of Lightbird when we get it, right?
Yeah, and I understand.
Yeah. The low northern variance, and you can ask, well, why? Was this measured at n side of 16? Why ecliptic? But we also, by the way, this ecliptic is not optimized. There's also a low northern skewness and a high northern a high kurtosis. So there's other things that are odd about the statistics, which aren't well correlated with the low northern variance. The parity preference that I quoted for you, it was a really dumb statistic, okay, that they chose. What they said is, let's measure the ratio of the odd power to the even power. Okay? So remember what was happening is that the power in the odd multiples was always greater than the power in the even multiples. So think of that as 1 and 1 plus epsilon. Okay? And now make that 2 and 2 plus epsilon and 3 and 3 plus epsilon, and their statistic goes to 1 and you lose all significance. What you would have thought is that the correct answer was 1 over 2 to the 9 because there were 9 straight pairs, and then let me give you a look elsewhere penalty of 2, which is about a factor of 10 worse than this, more anomalous than the statistic they chose. So they did a very bad job in choosing their statistics.
So why
Yep.
aren't those anti-correlated because of the galactic cut? I mean, there's an intrinsic correlation there, right?
It doesn't seem to come out of the galactic cut when people have modeled it. Okay. Quadrupole octupole alignment. It turns out that there are other multiples that are also correlated that most of the people stopped talking about because it felt too much like tea leaf reading, and people just kept talking about L equals 2 and 3. Okay. So if you go and try to figure out what are the look elsewhere penalties, they're probably somewhere around a factor of 100. And the look more closely rewards are somewhere like factors of 10 to the 5 or something. Okay, so, and we could go do an exhaustive analysis of those 20 statistics, the BIPOSH statistics and the genus statistics and all those, the Minkowski functionals, and some of them will be correlated and some of them will be less correlated, but it's not going to get better than like 10 to the minus 8. All right, so there is strong evidence, and Nyash wants me to say, that the universe is not Gaussian random statistically isotropic, and I'm going to say to you that a lot of these things are not just Gaussian, unless by Gaussian you include that I get to put non-zero means for my ALMs. Okay. And I don't think that's what I mean by fluctuations. What do we do when we're faced with a situation like that? So of course, the thing we really want to do is find a fundamental physics model and make testable predictions. And I'll talk about that very briefly in a minute. The other thing we want to do is make reasonable phenomenal extrapolations and test them. So for example, everyone has lied to you when they've told you that the angular correlation function is close to 0. Because what's really close to, including me, because what's really close to 0 is the dipole subtracted angular correlation function, because that's the only thing that we know how to that we really know. Because we know that the dipole, if it's due to our Doppler, our motion through the universe, is huge, and so we just throw it out entirely. If you want to not spoil the smallness of S1/2, you have to have a cosmological dipole that is really small. Okay, so that's a testable prediction. I don't know if we can test that prediction, but that's an example. And there are other testable predictions, like, for example, if there's physics behind S1/2 of TT, perhaps S1/2 of EE should be small, and by that way, that's something that people said before people went out and tried to measure S1/2 of EE. Okay. So what do we need from a model? Okay. We need it to break statistical isotropy, including, by the way, parity, if you notice, which probably means breaking statistical homogeneity. We need it to affect scales that were until recently causally disconnected. Okay? Or to somehow do everything at low z, even though we have a signal that we started with at high z. So somehow the low z physics would have to fix, well, undo what we had at high z. Okay, I'm now into my imaginary time. I'm almost done. And this is a real problem, because the consequences of a broken statistical isotropy, of a broken rotational symmetry, is that it no longer protects all sorts of things that we have used it to protect. So for example, statistical isotropy is what forbids all the off-diagonal correlations of TTE, TE, BE, BB, and TB and EB. Okay? So you break statistical isotropy in a parity, everything is non-zero in principle. Right? So our whole picture of what our correlation matrices look like is different. Okay? We have a general correlation matrix. Some of those require a parity violation, but we already see that. Many of them don't. And so there's a lot more information in principle that we can extract, but it's much more difficult to extract because it's distributed all over this correlation matrices. What are the new models known to explain all or most or several of the anomalies? I think that's the list. Okay. But what I do know a physics phenomena that's already in our theory that breaks isotropy. And by already in our theory, I mean it's in GR, we just haven't used these boundary conditions, and that's non-trivial cosmic topology. And you can look at this very simple example of non-trivial cosmic topology, namely a periodic box, and realize that it's not statistically isotropic. Okay. So what I've tried to convince you is that the CMB is not the realization of a Gaussian random statistically isotropic field. I didn't just slip that in, Nayash, now. The universe is not statistically isotropic. Okay? The cosmic orchestra may be playing a ΛCDM symphony, but somebody gave the bass and the tuba, and if you ask me about it, also the piccolo, the wrong score. They tried very hard to keep it quiet. They failed, and we really need to find an explanation. There's no proven models so far. It seems very hard for it to be systematic, not when Kobe, WMAP, and Planck are all seeing the same things. Foregrounds is really hard to get it to look like this because foregrounds are foregrounds, and they would have to undo background signals. If it's cosmology, it could be topology, but I haven't told you how topology produces precisely the correlations we've seen. And I promise you, if we had found so far a model in which we had found that, I would be standing up here and telling you about it. Okay? Or something else. But in the meantime, we're spending a lot of time going back and improving the Planck search for the topology of the universe, which was good, but left a huge amount of parameter space on the table. And we know how to fill it. And we think that LightBird will do an even better job. And maybe some of the things that come between now and LightBird. And I think that's exciting science. And I want to encourage both people who are interested in data and people who are interested in theories to think about this, because I think it's very puzzling and very important. Thank you.
Well, given that you haven't found yet topology model which suppresses correlation on large scale, you would think that in zero approximation, topology does opposite, that it correlates. I know. I know, but.
And I know that that's not necessarily true. In fact, I think you probably know as well as I do that there was a Nature cover article, right, claiming that the Poincare dodecahedron as a topology would predict a C2, a C3, a C4, and exactly the right ratio in order to give you S1/2. Now, for two reasons I didn't believe that paper. First of all, that particular model was already ruled out when it went to press for reasons of publishing in Nature. But second of all, I don't really believe predictions of C sub L at very low L in topologies because it's not clear that we trust the power spectrum at the Ks of the size of the full topology, right? Yep. So I think it's going to be hard to predict S1/2 reliably.
Yes, but what I want to say is that naively, you would think that in a topologically compact model, you expect some correlation at large scale. Therefore, maybe in some model, you get a right compensation, but it is even less probable than in a isotropic.
No, it turns out to be, it turns out what seems to happen, at least when people have looked at slab models, for example, what typically happens is that the Sachs-Wolf gives you a lower S1/2, and then the ISW ruins the solution. So I think the thing that we have intuition about actually goes in the right direction, maybe, that it gives you the right answer, and then the integrated Sachs-Wolf ruins it, right? So.
Question there. Okay, there have been tests of isotropy using many different data, right? I mean,
many different CMB data, or you mean other data?
CMB and other data.
Okay.
Okay. So, and they don't find exactly the same thing, right?
Well, the CMB data find exactly the same thing.
No, CMB among CMB, yes. But
yes.
the CMB and the other things doesn't find exactly the same thing.
But,
so,
what do you mean? I mean, do you mean, how do you use the same statistic on?
No. I don't find a very good connection between the signal of an isotropy between, let's say, quasars and CMB, right? That one can connect them.
CMB is at redshift of 1,000. The quasars at redshift of 1.
Yeah, I mean we're at different scales. It's not clear that it's not clear how to compare them yet. But this comes back to that statement that we should, if we had models, it would be one thing. And I can tell you, I'm kind of jumping in before you finish your question.
I didn't finish my point.
Okay, go ahead.
So I agree that there should be a model, right?
Yeah.
I mean, but if you're talking about the different things, right? If the CMB anisotropy is different than what we find the quasar anisotropy, it looks to me that we are looking at so many unknowns, right? And ruling out systematics altogether looks to me a bit too far. I mean, I would always keep systematic as a part of the game. I mean, at least in some of the data.
Sure, you can absolutely say that. You should go and figure out how WMAP and Planck ended up with the same systematics, because all these statistics are in both maps.
I'm not necessarily talking about CMB. But I'm saying, if I want to model everything, right?
I think it's been very difficult up to now. How many low redshift, meaning much less than 1,100, data sets have we had in which we've done a good job at understanding angular correlations above 5 degrees? How many?
Yeah.
None. I think the answer is none. Okay, so most of the signal at the moment in the statistical anisotropy, the CMB, is at low L. Now, not all of it. There's this very weird thing that if you look at dipole modulation, right, and you go fitting in L bins, okay, and you march those L bins up, okay, you'll find that the statistical significance of the amplitude rapidly goes away. I think it's by depending how you do it, by about 100 or so. But all of the directions keep lining up for a long way. But
I'm not against it, right? I mean, I have a paper with a p-value of 0, right, with the Yashar, and that's totally fine. All I'm saying is that we should still have a little open mind.
Look,
I'm not going to rely on everything.
We should always have an open mind, just not so open that our brain falls out. Each of us has to decide how open that is, right? I think you're right. We have to have an open mind, and if you have, just like I think other people should go ahead and work on theoretical models for the physics. Someone, not me, okay, should go look at models for the systematics in which they identify a systematic problem or a foreground. And look, I think for example, the work that that Frode Hansen and his Argentinian colleagues have been doing is very interesting. It's really hard to make it a solution, actually, to anomalies, it tends to exacerbate them, but it may change their story. So for example, it may mean that if it turns out that it means that all of the low L signal comes from wrong sign ISW, from low Z, CMB passing through low Z structures, and so in fact, all the low L ALMs were 0, then there may be a different explanation for that is not statistical isotropy violation. It's something completely different, maybe. Exactly how that, but how that ends up with low northern variance is not so clear. How that, how it can, so you end up with a different tension with lambda CDM, right? So.
Okay, last couple of, Shubir and Dick.
Just a quick comment. You mentioned the possibility of a cosmological dipole, small one. That's, of course, argued against by what Tarun mentioned earlier, the correlation between the higher multipoles, which is consistent with aberration to some extent, I think.
Oh, no. What I mean, I don't think Tarun is saying that we've measured. What I mean is that we would have to go and measure, using what Tarun has talked about, the correlations between the high L's. Yeah. We'd have to measure the velocity, our velocity. Exactly. And then we would have to subtract that from the dipole. Yes. Right? And we would have to see that the difference, which we would call the underlying cosmological dipole, is is small, is really small.
It's 0, in fact. It's within uncertainties. The uncertainty is still of the order.
Yeah, the problem is the uncertainty is too big. No, right.
But I wanted to say there is one more data point, which is that WMAP also measured the spectrum of this dipole component, and it is consistent with being the derivative of a Planck spectrum. Yeah. Also to within about 10% of thing.
Right. So what I'm saying is, in fact, the opposite. I'm saying that those two things need to be very consistent.
Absolutely.
Right. I forget the exact number. It's in some paper of ours.
The limit of how good that measurement can be, but perhaps
I'm not right. It's so we would have to.
But it should be 1% or better.
Right. We have to measure it to 1% or better, and then it turns out to be even a little bit smaller in order to not spoil S1/2.
Yeah, but you can't get. I'm saying that we haven't got to that point.
No, we have not got to that point. I don't know if we can get to that point. I don't know that anyone's done a good estimate of whether we can get to that point.
Okay, so it may sound like I'm not enthusiastic about this. This is completely wrong. In fact, as you saw as my set of figures passed, one of the things I highlighted was, in fact, the anomalies. The one I haven't paid, that I should have paid more attention to, the rest of this one has. Xijing Wang and I, we've had this discussion before. We tried very hard to come up with a grand unified theory of anomalies and couldn't. Of course, now, what's on that figure, and I'm going to explain the figure for a second. What you can do is to take one's favorite model, LCDM, determined by the, am I not on?
Oh, we heard you.
Yeah, I speak loudly. I'll speak even more loudly now. Everybody wait. You can do Wiener filtered maps that will continue to show the phenomenology, but what you've done is to take away the oscillations associated with BAO, et cetera. And so that's a very useful way to look at it. And the anomalies come through loud and clear in exactly that framework. I haven't checked what happens with S to the half, but that's an interesting thing to do because, we're pretty keen about these. What I have is ping pong theory question mark, because instead of being as radical as the ultimate ping pong, which is topology, you might be able to just have some phenomenology of the form that I was talking about that stretched things in the inflationary period that created a signal that does give you the near zero. I haven't done that, but I think that that's not improbable. But I'm going to end on a really interesting phenomenon that people in the room might not know about. All of this enthusiasm radiated out of CETA back in the mid-90s.
And one seminar by Igor Tkachev.
Exactly. And so all of the different people that went off into topology and then did all of the statistical isotropy breaking work, it was all because we were in this one seminar in this relatively small room at CETA. So he was there, he was there, he was there, I was there.
No, Tarun wasn't there. He came a couple of years later.
Oh, you mean we indoctrinated you?
But Jana was there, and she went off and got Joe Silk and John
yeah.
Barrow interested, and
Yeah.
Neil was there, Cornish was there,
Yeah,
and
no,
we got David Spergel interested. And,
Yeah, no, so it was.
And the exception is the French and the Germans. There was a French.
But they were soccer balls, so.
I do want to say, you kind of, so I think, I'm not, as I said, I'm not saying topology explains this. I do think, one of the things we're now learning, and hopefully, I was hoping I'd be able to show a graph, but we have to maybe by the end of the week, we have to double check that it is as converged as we think it is. That actually there's, not surprisingly, in principle, a lot more information in surveys eventually and line intensity mapping. So with CMB, we can, so right now we know the shortest distance, in terms of topology, we know that the shortest distance around the universe is bigger than 98.5% of the diameter of the last scattering surface. Sorry, the shortest distance around the universe through us is greater than 98.5% of the diameter of the last scattering surface. With Planck, we should be able to push that, depending on the topology, out to somewhere between 1.05 and 1.3 in some very special topologies. It looks like if you really went after and got did the line intensity mapping as well as you really want to do it eventually, and that you might be able to push that out to 10, which is really surprising. Certainly to 4. Okay. And we were surprised at some level, but it really does seem like the information can, in principle at least, be extracted. And now the question is going to be, in practice, how hard it is.
So can I give one little anecdote that is, I think, germane? When we try and model the dust distribution in the galaxy, we went over into actually the occupation matrices in order to better determine it, and then everybody's now adopted that. But what was necessary and what continues to be necessary is that you have to, unfortunately, take the low L sky and essentially use it as a constraint upon which you do the higher spatial frequency fluctuations. So we could be stuck with the situation of that's just the way it is, and that's a constrained field that just happened to arise. And I agree that it doesn't fit into the sort of root mean square fluctuations of a Gaussian random field, which I think it does not. But, we could end up in that unfortunate situation. And so what we really need, as I've said and you said, we need a grand unified theory that brings them together and takes, a couple of sigma things and pushes them way through the roof.
Right.
And I don't know what that is. You don't know what that is. And you've been thinking about it for a long time. I've been thinking about it a long time. He's been. And maybe that will be the way it is, but that will be a real shame because it's there, you can see it. Sometimes my good friend George Estathio has looked at it and says, that cannot be. And certainly some of the WMAP people had that view too, but I think they've come around, actually. Bennett actually thinks it's there now.
Right. Even George said to me after a seminar recently, this is really weird, Glenn.
I can remember talking with Chuck before we launched.
Yeah.
Looking at it and just saying that there's something really different between the north and south. So that's always, I agree completely, it's always been there.
Yeah.
Okay, so on that note, let's thank Glenn and all the speakers for the session. Break for tea and then come back to the discussion.